Hello guys, welcome back to the LearnRISC-V channel. I'm going to discuss and demonstrate how to time multiplex a more than one task in RISC-V assembly. So till now, if you go through the apps or the tasks in the Git repository, all these apps are just one single loop of execution. It just performs one task. For example, the LED blink code would just blink the LED, and your transmission would just transmit the UART data in a single loop. And there is also an example to demonstrate the machine timer, like generating a timer at a set interval. Okay, so if you watch all these tasks, let's take an example for the LED blink. So right after the reset, so the execution will jump into the start entry where the stack pointer and the machine trap vector are set, and then the execution will jump into the LED blink code or the app entry where it just configures the set of registers in GPIO, and in a loop the LEDs are turned on and off after a delay. So this is the one loop of execution that a processor would be executing. Okay, and in the UART TX example, it's the same, except that right after initializing the stack pointer and machine trap vector, the app would just configure those registers, and in a loop it would just keep sending the or keep transmitting data through the UART port, and at no point the execution would jump from this UART task to another task or anything. Okay, so for the machine timer example, so what the example code would do is right after configuring these machine timers. Okay, this is wrong actually. This is for machine timer we don't configure these registers, whereas just the timer registers has to be initialized. Then a timer interrupt or the machine timer would be generated at a periodic interval, whatever we have configured it for. Okay, so I'm just going to demonstrate how we can multiplex more than one task in RISC-V assembly. So what I have done, or what I'm gonna demonstrate is use the machine timer to generate a periodic timer for every 5 seconds, and at the very first interrupt it would jump into the LED blink loop or LED blink task, where inside which the LEDs would be blinked on and off for 5 seconds. Then in the next interrupt, or in the after 5 seconds in the next timer interrupt, the execution would be switched to the UART transmission loop, where a UART byte would be transmitted through the UART port. Okay, then it would be toggling or switching between these two tasks for every 5 seconds. In other words, each task would be executing for 5 seconds alternatively. Okay, this is just a primitive task switching. Okay, let's see how it works. So before we get into the code, it would be easy to understand, to watch what is that we are trying to achieve with this time multiplexing of these two tasks. One is the UART transmission. So these waveforms, so one is the probe on the ground. You can see on the video the black probes. The brown one is the one that's connected to the ground, which is this, and the blue one is connected to the UART TX pin. You can see here it's high, that means the port is enabled, and every time there's a data transmission it would send, and the moment I click this it would capture the signals on these two wires. Okay, and at the same time you can see the LED blinking on the board. So let's capture for next 20 seconds and see what happens. Okay, now if I zoom out and see the time interval between these two spikes, it's 9.99 or 10 seconds. Okay, so if you observe carefully, what would happen is, or once we get into the code it will be more clear, but what I'm doing in the code is 5 seconds. So the UART transmission loop would be executed, but in that 5 second it would just transmit uh, a single byte, which is I'm transmitting the ASCII code for A, which is hex 41, and then it would just wait in the, let me go to the code for a minute. If you see here, so inside the UART loop, we will come to this code later, but just want to show that inside the UART loop, the hex code for uppercase A, hex 41, is transmitted. Then it would just be looping here. And on the LED blink code inside the loop, it would just on and off after a certain delay. Okay. So now, before we get into the code, let's capture once again. You see now that the LED is blinking for this blink, this would blink for 5 seconds. Once it stops, the first byte is transmitted. So next 5 seconds, the execution will be in the UART loop. Then it would jump into the LED. Then the LED started blinking. Then when it jumps back to the UART, then for 5 seconds, it would be inside the UART loop where it would just transmit the first byte. So now let's get into the code. So first I just want to mention that if you go to the Git repository, and so LearnRISC-V, this is a Git repo I use, and if you go to the development branch, and you can see the latest commit in apps directory, which is the dual app. Okay, and so the same code whatever I have in my local repository I have already committed, so you can see the code on the repo, but I'm comfortable in using our showing the code in Visual Studio Code. Okay, so The dual app has 3 files. So one is the main.s, other one is the blink.s, and third one is the what_tx.s. And to build this, you need to issue this command that is like /build.sh, and board option is -1 revision B, and the dual app is the app option. So that would basically build all the files inside this directory. And now going back to the very first slide, as I mentioned here, so the execution when you build this dual app would be like this. So right after the reset vector, inside the start.s or the start entry point, the stack pointer would be initialized and the machine trap vector would be set up. Then it jumps into the app entry, which is there in the main.s file inside the dual app directory. And this, from this entry point, the LED blink initialization followed by the what_tx initialization is done. So that I think it's worth mentioning to note that these two apps are mutually exclusive. That's why I'm able to jump and both the task works, though we don't take a backup of any of the state variables or registers in this tasks. Still it works. That is because they are mutually exclusive, and for now, to make this appear simple, I have discarded all those. I have assumed that these tasks don't have, the state variables don't have to be stored. Okay. So now, let's go to the start. Yeah, so right after reset, the stack pointer is set here, and then the machine trap vector is set here. Then all the interrupts are disabled very first, and later whatever based on the need it would be enabled. But then after this, it jumps into the app entry. And in the dual app, the app entry is nothing but it would come here, and as mentioned, very first it calls or sets the initialization of the blink LED task, which is this one. It has to configure the set of GPIOs, and GPIOs should be set as output, and whatever the configurations that is needed for the LED to blink, that is done, then it would return. Same after that, then it would call the what_tx underscore init function. If you go to the what_tx init function, it would set the baud rate, configure the GPIO as IO functionality, which is UART, and it set the stop bits, and what else? Then it enables the UART. Okay, this all happens in the initialization, and at the end, the loop, inside the loop, it would just send a byte and then loops inside the set. Okay, and in the blink code, after initialization, there is a loop which would write 1 and 0s after certain delay. So this would be like a LED on, and there's a delay, and then LED off, and that's a delay. So if the execution jumps here, then this would be looped forever unless interrupted by something else. We will see what that is. Okay, so once this initialization is done, then you see the machine timer interrupt is configured, and please be informed that this machine timer interrupt is as per the manual. I see that this is something that you use it for one-shot timer, but I have used it to generate periodic interrupts. So what I do is this timer interrupt would be generated only when the m time compare register, let's say that at the very start the m time register would be 0 and the compare register would be written as 5 seconds, or the values that is equivalent to 5 seconds. If you see here, so this is the value, because this is the clock and clock speed or clock rate, then into 5, this is the value. That's what would be written into the compare register. So whenever this m time value would be incremented based on the clock rate, and then once it reaches the m time compare, the interrupt would be generated. So after initializing all the other two tasks, and once the timer is configured and enabled, after 5 seconds, so the first interrupt would occur and it would jump into the machine timer app handler. So if the interrupts are not generated, if you see here, then it would be just the execution would always be. So this is just jump space dot is an easier way of writing the code to keep the execution at this point, or like it's like equivalent to jump or loop here forever. Okay, so after the first 5 seconds, the execution jumps into the interrupt handler or the machine timer interrupt handler. And if you see here, what I do here is, so this m time, once it starts incrementing, so there are two registers, one is the m time and the m time compare. So whenever the m time reaches the m time compare, it's going to be a one shot interrupt. So what I do here is I add another 5 second the add an value which is equivalent to a 5 second to this m time compare register, so that inside the handler, so that this timer interrupt is active and it would occur every 5 seconds. Okay, and I use if you see here, I use S0 register as a as a flag to switch between. So very first, this is 0, so if f0 is 0, not equal to 0, jump into UART loop. If it is 0, so LED blink loop. So it would jump into the, or it will load. How does it jump? So if you jump into blink code from the trap handler, then the next interrupt can never occur unless the trap service routine is processed. So what I do here is, if you see here, I don't jump into the blink loop. Instead, I just load the address of the blink loop to the mepc register. Okay, and this one is, and toggle the flag so that next time it goes into UART. But the importance of this one, like writing this address of the blink loop into the mepc register, is that what would happen is, whenever the trap routine is finished, when this mret or return from machine trap is executed, whatever the address that was there inside the mepc would be loaded into the PC program counter, and the execution would jump there. So for the first time, since I have loaded that into the loaded the address of blink loop code, which is on and off of the LED, that would execute. And after 5 seconds, and the second time this timer interrupt would occur, and from this loop, since it's an interrupt, excuse me, so the execution would jump into the interrupt. And if you see here, since I would have toggled the flag first time, the second time the execution would go to this part of this section of this block of code where the address of UARTX loop start is loaded into the mepc, and then I would return from the machine trap handler. So if you go see what happens here is, it's nothing but the same UARTX loop, where it sends the first byte and it loops here forever until it's interrupted. Okay, So now if you see this, so the main thing that I would like to emphasize again is about the to switch here a direct jump, or you cannot do a switching without writing into the mepc register. Okay, and so this is the code which is submitted into the GitHub repo, and that's it. And if you have any queries or any comments, please put it on the comments below. I'll gladly help you out, or if there is any problem with the code, I will fix it up. Okay, thank you very much. See you in the next session.